Welcome to Water Science for Everyone.
Have you ever wondered how hydrogeologists quantify an aquifer's capacity to store and release water? Understanding this fundamental property is crucial for managing our precious groundwater resources. But what makes this measurement so unique, especially its unitless nature? The aquifer storage coefficient, also commonly known as storativity, is indeed dimensionless. This is because it fundamentally represents a ratio of volumes, specifically the volume of water released from or taken into storage per unit surface area of the aquifer, per unit change in hydraulic head. When you express it this way, all the units effectively cancel each other out. Let us explore the why behind this. For a confined aquifer, storativity is a measure of the water released from storage due to the elastic compression of the aquifer matrix and the expansion of the water itself as the hydraulic head declines. Imagine a column of aquifer material with a unit surface area. The volume of water released from this column when the head drops by 1 unit is the storativity. Since the volume of water released has cubic length units, and the product of the aquifer's surface area and the change in head also has cubic length units, the ratio becomes unitless. This is often linked to specific storage, which is the volume of water released per unit volume of aquifer per unit decline in head. For an unconfined aquifer, this concept is similar but dominated by a different mechanism: gravity drainage. When the water table drops in an unconfined aquifer, water drains from the pore spaces due to gravity. In this case, the storage coefficient is practically equivalent to the specific yield, which is the volume of water released per unit surface area of the aquifer per unit decline in water table. Again, this is a ratio of a volume of water to the volume represented by the aquifer area multiplied by the change in head, resulting in a dimensionless value. This dimensionless nature is incredibly useful in practical hydrogeology. It allows for direct comparison of water storage capabilities across different aquifers, regardless of the specific units used for length or volume in a particular study. This simplifies complex groundwater flow equations and ensures consistency in hydrogeological modeling. It means you can apply a storage coefficient measured in meters to an aquifer represented in feet in a model, without needing conversion factors for the coefficient itself, only for the other parameters. A key advantage of this dimensionless characteristic is its role in applying analytical solutions like the Thies equation, a cornerstone for analyzing pumping test data. The dimensionless nature of storativity prevents errors that could arise from unit inconsistencies when dealing with various parameters like time, hydraulic conductivity, and well discharge. While hydraulic conductivity, for example, has dimensions of length per time, storativity stands alone without units, making it a universal quantifier of an aquifer's storage response. Ultimately, understanding why the aquifer storage coefficient is dimensionless helps hydrogeologists accurately characterize groundwater systems. This clarity facilitates more robust predictions of aquifer response to pumping, more precise assessments of groundwater resources, and ultimately, more informed decision-making for sustainable water management. It is a testament to the power of ratios in simplifying complex natural phenomena.
If you love learning about water, like, subscribe, and keep exploring with us.